Well, our next speaker is Mr. Subramanyam. I don't think he needs any introduction. A senior colleague of mine, we have been working together on the LCA program. But for the purpose of completing the formality and for people who do not know him, he is a mechanical engineering graduate from NIT Warangal and a postgraduate in aeronautics from the Indian Institute of Science. He is a distinguished alumni of the Indian Institute of Science. He has been in the DRDO from 1975, starting his career from DRDL, working on the Integrated Guided Missile Program. And then he came to ADA, that is the Aeronautical Development Agency, in 1986, and has held various positions. He has been instrumental in bringing electronics and a large-scale flight control system and everything on the LCA as a platform. Very recently, we have achieved the one major milestone on the light combat aircraft program. That's the achievement of the initial operational clearance. On 10th of January, the defense minister came for that function. So he'll have a lot to share. I hand over to Mr. Subramanyam.
Shri N.C. Agrawal, my colleague, the fellow speakers, Shri Natarajan, and the distinguished participants of this particular seminar. Good afternoon to all of you. I'd like to thank the organizers for giving me this opportunity. The speakers before me spoke about the higher layers of the system evolution. The threat scenario was discussed. Some kind of mission analysis is discussed. Then strategies to design globally was also discussed. But I think I'll try to become down to earth, how really we go about designing it. Especially, my aim is to focus it a little more on the young scientists and the students so that they'll absorb the things which I'm going to talk, which may not be going over their heads. So that's how I have structured my particular talk today. The design of an aircraft actually starts, as I said, the threat analysis will have to be done, mission analysis have to be done. Finally, the user and the government will specify, okay, fine, this is a mission for which the aircraft has to be designed. And that's where the challenge for the designer starts. Thereafter, we'll see how the design has to be done globally with cooperation or with whatever strategy that the individual country would decide to have. I'll just go over a couple of missions. One is the air-to-ground, which I have taken here. Starting from the left bottom, the first one is takeoff segment of the mission. The requirements sounds simple, short takeoff. And we'll see what it means, technology in terms of engine, etc. The quick reaction system, this is what is an evolving thing. Every time we are told, see that the aircraft can get airborne after a command within the shortest time. That demands technologies. And the user would like to have the pre-flight checks done, absolutely nothing undetected, nothing spurious told. So that's how the demand comes to the designer. Then the next phase is the climb. The different types of requirements, probably a minimum time to climb to a particular altitude, or sometimes minimum fuel to climb there. All these things would lead into the design and technology challenges. Then comes the mission segment, cruise in the case of a strike aircraft. Each of these bullets is really a challenge to the designer. And this is where a continuous evolution of the future technologies is going on. The low observability, the maximization of the range, and the super cruise, that is flying the aircraft in the supersonic speeds without the afterburner on, is a kind of requirement from the consideration of again to some extent low observability, and then the mission performance. And a powerful radar, maybe it's AESA or its future versions of different apertures all around the aircraft and still getting the signal. And good pilot associate, it's something related to the artificial intelligence where the pilot's workload is reduced. The missile warning systems, the precision navigation, and so on, the list goes here. Okay. I will not get into the details, but I'm just indicating that's how the demands come to the designer to design the aircraft with all these things. Unfortunately, down the line we'll see all of them are not, let us say, coaxial. They are all sometimes antagonistic and lead to the conflicts of design. That's where the design challenge comes. The next segment of the phase, the strike, and the requirements are indicated as perceived by the user. Then comes the egress phase when they come back, and that closes this particular mission. Then another mission, probably some of the segments it remains the same, but especially here the requirements of the combat air patrol and the air combat requirements will be slightly different, demanding the higher maneuverabilities of the aircraft and the reduced sensor shoot time, which is very important. The reduction is almost going to a few seconds. Good flight directors, what I mean is the flight guidance is a thing which is coming up both in the close combat as well as the BVR missile combat. Once a threat is detected, what kind of algorithms to be used on board the aircraft so that a differential game logic is employed and our aircraft gets a gain over the adversary aircraft in terms of positioning for firing the missiles. And of course, the other things which I've indicated, efficient identification, etc. This is how the designer first breaks up the segments, arrives at various user demands. Now, that would start demanding from the designer what he has to do. I forgot about the next very important one. Along with the missions which we have indicated, the user would also impose the stringent requirements of the maintenance and operation, which is very, very important in terms of the overall life cycle cost of an aircraft. This plays a very significant role, and these requirements are given here in terms of the high availability, ease of maintenance, and reduced operational cost, and so on and so forth. And what technologies are demanded to achieve that are given in the bottom block in terms of standardization and newer techniques of integrated vehicle health monitoring and MEMS and MOMS based prognostic and diagnostic systems, where a good amount of research is going on and many people in the country are also working on that. Okay. And down the line comes the applications that have to be developed for ease of maintenance, which are computer based. These are all the things which are required from the maintenance and operation requirements. So start breaking down and getting little more deep into the details. A pre-flight built-in test, that's what I said. It sounds simple, but it is a complex job for all the system designers. You would find out a complex system with almost, I think, say 15 to 20 major subsystems on the aircraft. He has to find out algorithms which would detect even the minutest fault on this thing. That's the highest probability of detection, and never throw surprises in terms of false alarms. It's a continuously evolving technology so that we clear the aircraft with high probability of detection and low probability of false alarms. Other things which aid for the takeoff phase of the mission is the alignment times and system initialization. There's a continuous requirement of alignment with a shorter duration with higher accuracy and minimum time to be used for that. The short takeoff distance will always look for shortened takeoff distance. That's where we get into technology of thrust vectoring and high thrust engines and the techniques of reducing the thrust through, which normally occurs in the initial phase of the engine, and some special technologies to see that for the phase of the takeoff you get a special feature so that additional thrust is generated. And in terms of the landing, the demand is on the optimal anti-skid brakes so that the landing distance is reduced to as low as possible. And the new challenge that we are seeing in the programs is integrated brake and flight control system. People who have worked on these areas know that there is a coupling between these two, and the technology is demanding to have an integrated approach for this design. And in the areas of the climb related, of course, the basic aircraft design is one element, but also the new requirement is to generate onboard in situ optimal trajectories in terms of the time to climb or minimum fuel for climbing. Then comes the most important phase of the flight, which we have seen earlier. It was said, okay, low observable, but once you decompose it, it becomes rather blown up. It means low radar signature, which would demand the bullets which are given there, look for the radar absorbent structures, materials, and paints. All of them are now technologies by themselves. And again, for the low observability, the serpentine intake and exhaust, the design itself is a challenge, especially the serpentine intake, without losing what we call the pressure recovery. Low infrared signature, because as we know that in the area of threat detection, it's not only in the area of radar, but in the area of the infrared detection also, there are substantial improvement to detect the enemy threat, which only means that you should have an aircraft whose radar signature is as low as possible. That again is a challenge in terms of the aircraft engine designers, especially on the nozzle side. Then, of course, speakers earlier to me have already impressed upon the requirements of the net-centric warfare. It's very, very important, and it's a technology that is continuously evolving. We have to catch up with that also if you have to have a good system design, that is aircraft and the surrounding systems which are cooperating with the operative segment. The supercruise demands, as I already said, what a supercruise. It looks for a complex engine design which would definitely give the thrust as much as possible at the dry power itself, okay, and still giving what is required at the max afterburner level, which again meets the mission requirements. This is a challenge. And of course, the other one which is mentioned here. So on the advanced mission, mostly avionics supported requirements are indicated here. And when we come to the combat mode, it's a well-known thing that super maneuverability is required, that is integrated flight and propulsion control, and of course the advanced sensors and weapons is a requirement, and there are continuously evolving challenges in this area, which I have listed here. Some of the things which are coming up is really a fifth or sixth generation is the directed energy weapons. I'm sure one day they will become a part of the aircraft weapon system. So I just analyze, now comes the challenge to the designer. All those requirements which are pouring into the designer in terms of various demands. For example, we take an unmanned aircraft. It has the demands on the aerodynamics, the stealth, and the flight control. And if you look, all of them, the solution is not going to be simple. It's going to be complex because the requirements from each of them are contradicting each other. That is where we get into a subject. It's enabling technology. The multidisciplinary optimization is a new technology which is evolving, which would support the design of this kind of conflicting requirements from various sub-disciplines of the aircraft. And that is an emerging area of technology. A lot of progress has been done even within the country in terms of evolving these tools. It's not simply buying an MDO package, but you have to characterize specific to the application which you are working on. This is one area where the technologies are evolving. So just to take one simple example, okay, if one takes the design of an unmanned aircraft, the left top one which indicates if nothing is done on a flying wing, how the pressure distribution is that. Then the challenges from the design comes, okay. One is they would like to have a broad band of the angle of attack where the L by D is adequate for the mission fulfillment. Similarly, they would like to shift the pitch up which they get to the right. That's again a complicated aerodynamic design. And of course the maximum CL. What I'm trying to say, many people may not understand. All that I'm trying to say is every stage is leading to complex contradictions of the design, and new design methods, design tools, and experimentation is required to accomplish such design objectives. This is one more example where the demand for the control arm, what they call pitch control arm, is demanded. When compared with large L by D requirement, this is clashing with that, and one has to go for optimal design so that both of them converge to some satisfactory solution. Another technology problem that the scientists are saying, yes, for the purpose of low observability, conformal carriage of the weapons is very important, but once you have that kind of arrangement, when the weapons have to be released, the flow analysis at that condition is quite complex, and a lot of activity has been initiated in the country to get an understanding of the flow patterns when the bay is opened and the weapons are about to be released, especially if it is supersonic. And yes, stealth we have already indicated is a requirement, but it further decomposes into many other technology areas in terms of the aerodynamic shaping, which was shown in the right top, how the cross-section of the aircraft at various stations have to be iterated to get the best shape of minimum radar cross-section, the intakes, the internal weapons which I have already discussed, and the advanced materials and paints which are required again for radar cross-section reduction. And in terms of the infrared detection or thermosignatures, what you need is to do in the engine nozzle area that's indicated in this. Also, there are requirements that the engine exhaust should be brought down as much as possible so that the visible signature also reduced. This is another challenge for designing an aircraft with the low observability. So further, little more details I mentioned here in terms of the radar cross-section control. As I repeated, I'm only trying to see that how when you go down and down, it becomes more and more technology challenges, and what kind of technology areas are in front of us which we have to master if we finally have to give a product which the user is looking for, from again top of threat analysis and the mission analysis. So further detail, one gets into the design of, let us say, intake. It itself is a very complex subject. Quite a few academic institutions are working on that. The flow does break when the curvature changes, and there should be new methods and innovative techniques of doing a flow control there so that the flow separation is almost eliminated and the pressure recovery is high. So you want a serpentine intake for RCS reduction, but if you don't have this kind of controls, it would yield a pressure recovery which is very poor. The engine performance would go down. So innovations are required in the area, and we have to have technologies to overcome this problem. So at another area of designing the platform of aircraft wing, and that's how the challenges, especially when we talk about the flying wings, we will be seeing a new technology altogether, which at least in India we have not seen, controlling with the drag-arounds. The very flow over that particular place is a complex thing, and the analysis tools and the experimental tools have to be advanced to overcome that problem. So we do talk about thrust vectoring, but it's not as simple. The right side one says that thrust vectoring solutions by vanes deflecting the flow. Of course, the standard swelling of the engine is all right, but that's becoming outdated. The new technologies are the swelling of the vanes inside, and yet another new technique is what we call the fluidic vector thrusting. This is what people are working, and we're also trying to see how to exploit this so that we get swift thrust vectoring, what again is required for best maneuvers and things like takeoff, which I said in the beginning. So that's about, I just went into some depth to say that, yes, what are the challenges in one area, but if you take any other bullet point, further go down, it really leads to the technologies that we all have to work in the future. In terms of the avionics, we have just put in bullet points the demands which come to the avionics designer to meet the requirements which I have projected earlier in the mission segments. There are two popular design strategies which are normally talked about. One is the open system architecture, which is very much used, and that's going to be evolving further also, wherein the obsolescence of the components or the systems within the avionics systems is easily combated. When I say easily combated, if you divide the whole thing into 4 layers, changes only at one layer will take place to overcome the obsolescence, not all the layers in terms of the physical system and the domain, etc. This is something which is continuously evolving, so that it in many areas, even if you look at the maintenance or the life cycle cost of the aircraft, this kind of technology is helping so that the obsolescence is brought down and easily the changeover has been implemented. And this is what popularly known integrated modular architecture. The inputs on the left, the processing aspect in the middle, and the right side is the outputs where they go. This technology is going to be the candidate for the future aircraft that are going to be designed definitely in India and abroad also. Of course, one can get into details of all the blocks which are indicated. But again, all that I'm trying to say is this is another technology where the solution is such that it's highly fault tolerant. Okay? Normally these days, any failure occurs on onboard electronic equipment, we simply have to remove and then replace, but it takes time. But this kind of systems, once in place, okay, they are fault tolerant by themselves. With about 20% extra hardware and software built into the system, even some failures occur in these avionics equipment, you don't have to remove the equipment, it automatically reconfigures itself, okay, bypassing and dropping those elements which are not operational. That's how it's going to give the availability of the aircraft, okay, without frequent, let us say, removal and installation of the equipment. So, whatever time that I have found, I used it for the purpose of just telling the forum here how, after the higher layers of analysis of threat analysis, mission analysis, and design strategies are evolved, it comes down to the designers, and this great amount of technology evolution that has to take place. 1 or 2 areas I've gone into little more details, but each of that area is a complex design innovation by itself which is demanding. So these are the things which I thought I'll share with you before I conclude. Thank you.